young researchers and also young practitioners. We work to create a network among us and also to disseminate knowledge, of course, and try to include and connect young people to the world of the FIB, which is International Federation for the Structural Concrete. In this framework, we this year created this new webinar series, Concrete Affairs, which is basically a collection of online seminars that with the aim of disseminating knowledge and activities about Italian young researchers. And today we start with this first event. If you want to learn more about us or being updated about our events, you can have a look at our webpage. But also you can follow us on our social channels, so Facebook, LinkedIn, and also on our YouTube. This webinar will be recorded, and the recording will be available in a few weeks on our YouTube channel, so for your records. And now it's time to introduce the webinar of today. So today we are talking about development of integrated low damage building systems, an overview of recent investigations. So we will start, we have two speakers today. We start with a brief introduction about low damage techniques and some numerical investigation. Then we will see some experimental results. And then we will have a question and answer session. So all your questions, please write all your questions in the chat, and then we will answer all at the end of the presentations. The speakers for today, we have two brilliant young researchers. The first is Simona Bianchi. She is a postdoctoral research fellow at University of La Sapienza of Rome. She works on multi-criteria fragility-based design and assessment with a focus on non-structural components, but she has a wide knowledge about seismic assessment, retrofit, and also loss assessment, and especially she is an expert on low damage technologies. While the second speaker is Jonathan Ciurlanti. He's currently a postdoc, a PhD student at University La Sapienza of Rome, and he's working on multi-performance design of building systems, and also with a special focus on innovative low damage solution for concrete and also timber structures. Both of them, they have large experience in experimental testing, as you will see during the webinar. So thank you to both our speakers to be here with us today, and please, the floor is yours.
Thanks, Marta, for the presentation. So let me share the screen. Here it is. Okay. So, good afternoon, everyone. As Marta said, I'm a postdoctoral researcher at Sapienza University at the Department of Structural and Geotechnical Engineering. And there I'm working with Professor Pampanin, so maybe most of you already know him. So today with Jonathan, I will present you part of our research work. I will start giving you an idea of what we mean by integrated low damage building systems. And then I will go to some numerical investigations we developed. Well, this will be the boring part of today's presentation, while Jonathan will grab your attention with the most exciting part, that is the experimental testing. Now, let's start. So, think about a new building or a recently built structure, for example. What do we expect after an earthquake or a major seismic event? Well, if we were good designers, at the end, we are expecting the formation of these beautiful plastic hinges at the end section of our structural members and a beam sideway mechanism of collapse. So at the end, our buildings are not expected to collapse, but they can stand, allowing people to evacuate. If we look at the non-structural components, unfortunately, the situation is very different because in this case, they are not designed typically for seismic loads. So at the end, we can have high damage even in case of low seismicity events. So if we follow our traditional base approach, at least if we look at the structural part as per design capacity principle, at the end, this design methodology will lead to huge, substantial economic losses in terms of both repair costs and downtime. But today, in 2021, is this traditional approach based on life safety criteria still acceptable? Well, this is not enough because we need to raise the bar in earthquake engineering because we need to satisfy, let's say, the increasingly seismic demand from our society to create more resilient and stronger communities. And to do this, we need to shift from this life safety approach towards a damage control design approach by simply shifting our design objective towards a higher safety level for our structures. So by adopting this design philosophy, at the end, we can create buildings with controllable damage, and at the end, we can have reduced losses in terms of both, as I said, repair costs and business interruption. Following this goal, our idea is to create an integrated low damage building system comprising innovative low damage detailing for both the structural and non-structural components. Thus, these should represent the next generation of our building systems. Now, let's see a bit more about these low damage technologies. About structural components, we are focusing on the so-called press technology, precast seismic structural system. This system consists of unbounded post-tension attained pendants cables within the structural members and external mine steel, so-called plug-and-play dissipators. So at the end, we have our hybrid connections with a ductile behavior, and this connection behaves following this so-called flag-shaped hysteresis loop, which also allow us to have almost zero residual displacement after earthquakes. So this is a great advantage. So imagine we substitute the previous plastic hinges with these sacrificial fuses. These are the weakest element of this chain in this case. And after the earthquake, I simply go there, I substitute my damaged dissipators for a cost of 30, 40 euros per each, and that's it. So we have a lot of savings. So as Pampanino would say, we go to our seismic shop or seismic market to buy new dissipators for our houses. Now, let's see what happens about non-structural components. Well, in this case, we mean the introduction of low damage detailing. So we need to modify the connection system or the panel modularity of our non-structural components. So look at this masonry wall. In this case, we can divide our monolithic panel into vertical panels with internal and lateral gaps, and these can allow the formation of a rocking mechanism, so we can achieve a specific damage state with higher seismic demand, in this case in terms of drift, of course. If we use the same approach for drywall gypsum partitions, well, in this case, we do not add material or labor. In this case, we have the same traditional partition. We just need to modify the connection details, and that's it. Or another solution, we can add these dissipative connections, but we are looking later a bit more about these ones, so I'm not focusing on them. Or think about a suspended fully floating ceiling. Well, in this case, the simple introduction of this elastic insulation foam into the lateral gap can allow to achieve higher acceleration demands before these ceiling tiles can fall. Now, what about contents, which are very important to be safeguarded, as you know, in case of a strategic structure such as an hospital, for example? Well, in this case, we had the opportunity to test an innovative solution, a low damage solution, comprising supplemental damping within the system. So imagine we have our non-structural component, our content. We are going to attach it to connect it into our concrete floor slab by these anchors. So these post-installed fasteners, the traditional one, we simply add a ring around the threaded part of our rod. And at the end, by doing this, we can find high reductions in terms of forces and accelerations on these non-structural components. We found these in the range of 20–40%. And this was a research we developed in 2017, but was based on a previous one that was developed in New Zealand, in Canterbury University, before 10 years before, let's say, because the first prototype of this solution was already created. Well, this was also our first experimental test. So this allowed us to gain experience, let's say, in shake table tests, at least, and instrumentation, tested up everything. And this was very good for us to be prepared for the big experimental testing that will follow, which is this one. So by combining all the previous solutions, low damage detailing, we can create this integrated system with very high performance, and at the end we can have cost affordable technologies. And we had the opportunity to design and test such solution, but thanks to this European Horizon 2020 project. But Jonathan will explain better in detail everything. I'm not doing this now. Now, let's hear a bit more about the numerical investigations. Well, we implemented these studies in order to prove, let's say, the convenience of implementing such solutions. First of all, we developed cost-performance-based evaluations. So, a parametric analysis on reinforced concrete case study buildings comprising alternative structural skeletons, so monolithic low damage, frame wall systems, and non-structural components. And at the beginning, we studied the seismic behavior of this building configuration through a practical-based capacity spectrum method by using lumped plasticity models. And these, we could develop this model because one of the advantages of applying low damage connection is that the behavior of these solutions can be easily represented by macro modeling. So for example, think about this structural connection. In this case, in addition to finite, more refined, let's say, finite element modeling, or for example, the adoption of a contact element simulating the gap opening, the so-called multi-spring element. Well, in this case, we adopted, we can also simulate the behavior of this connection through these rotational springs working in parallel at the end section of our structural member, so beam, but also at the base of our columns and walls. As I said, this allows to control the connection behavior as well as the achievement of specific damage states, which in this case are the collapse of our external dissipators and the yielding of the internal post-tension bar. Now, what we found at the end of this parametric analysis? that we can have great benefits in applying these technologies, which was expected, of course, but not quantified yet. And in this case, we found a reduction in terms of expected annual losses in the range of 50–70%, while looking at the downtime in the range of 3 to 7 months. So think about the downtime. If we consider that we are working with modular, flexible, articulated precast components, at the end, we have a sort of Lego system, let's say. So we have a very fast time to build this typology of systems. So looking at the savings in the building life, we found these around 200 euros per square meters. So our building, which has a floor area of 500 square meters and has 5 levels, at the end we can have 500,000 euros of savings in the building life. So let's say a large amount of money to be saved. Then we implemented the same approach, so parametric analysis, considering low seismicity zones. And even in this case, we found great reductions in terms of losses by at least 50% when compared to the traditional monolithic structures. But the question is, why these advanced technologies are not so spread yet? Well, this is due to the fact that, let's say that these long-term economic analyses are not always implemented, unfortunately, in practice at least. And because there is always almost the perception that this technology would lead to higher costs. Well, this is true because if we consider the initial costs when this is when compared to a monolithic structure, this cost is higher in a range of 15–20%. But if we look at the seismic costs a long time, we can see that after 5 to 10 years from the construction of our building, this initial difference can be withdrawn, let's say cancelled. And after this point, we can have savings only, so a great advantage. Now, following the same research line, we developed feasibility studies for high-rise buildings, so to prove the applicability of these solutions even in this case. And in this case, we also considered the low damage dual systems. So look at how much we can decrease our residual displacements when compared to the monolithic structure. The residual displacement is a damage indicator of the loss of the structural safety and can contribute in increasing a lot our losses. So at the end, looking at the losses, herein expressed in terms of probable maximum loss, we see that the maximum repair costs goes from an 80% as a percentage of the replacement cost of the structure for the monolithic building to 30% for the integrated structure with the press technology plus external, let's say, low damage facade. Well, last but not least, we started to develop fragility and risk assessment analysis, and we are still working on this topic. We developed these studies to finalize our comparison, because by adopting this low damage detailing, we can achieve, of course, a better seismic performance. So we can move our fragility curves towards higher demand levels. Moreover, another advantage is that imagine that we have this fragility curve and this is our tailored, let's say, or our ideal response. Well, in this case, by adopting this low damage detailing, I can easily design my system to satisfy this behavior. Now, here this is just, let's say, a work we developed on non-structural components, in particular to study the global behavior of our system comprising precast concrete claddings with alternative connection systems, so traditional ones and dissipative ones. The dissipative is a U-shaped flexural plate. So these flexural dissipators that during earthquakes has inelastic deformation moving back and forth along this plate. So at the end, with this solution, we can even dissipate the seismic energy, and we can reduce our demand on the attached heavy precast panel. So while if we consider traditional solution, so this type of connections, these are designed to limit this interaction. These can be even less than 5%, especially at the beginning of our capacity curve, let's say. But these connections are expected to fail at drift level of 1.5%, while this innovative solution is not expected to fail for the achievement of a specific drift level, while it fails for fatigue criteria, that is, in this case, more than 150 cycles at the maximum stroke. So another great advantage. Then we implemented this fragility risk assessment analysis to highlight the seismic potential of such solutions, even in terms of probability of damage not being exceeded at higher intensity levels. Well, with my presentation, I want you to leave with two main messages, let's say. The first one is that there is in seismic engineering this need for enhanced structural seismic safety for our modern buildings. And this can be achieved by the application of advanced technologies, but even by the application of more appropriate design methodologies, for example. So these could create literally, let's say, this earthquake-proof building that the society is expecting. And another aspect is that we need to focus not only on structural components, but also to our non-structural components and contents to create these integrated high-performance building. And the other aspect is that we need to implement these long-term economic evaluations to really understand the benefits of implementing a specific solution. So I want just to finish saying that we are still working a lot on these topics, especially on the last part, in order to study the seismic reliability and the resilience implications of such solutions. So a lot of work is still ongoing. Well, here just few references about the previous work I showed you. I would like to thank you all for your attention, and I leave you in Jonathan's hand now.
Okay, now it's my turn. So cool. You did so well that now it's hard to replicate, I guess. So let me first introduce myself. No, so first let me share the screen, of course. Okay, can you see my screen, please? Okay, I think so. I'm Jonathan Ciurlanti. I'm a PhD student at Sapienza, University of Rome in structural engineering, as well as spending a period abroad within my PhD collaborating with the Advanced Digital Engineering Group at the Netherlands. And so today I want to just give you an overview about the experimental campaign we carried out last year in Lisbon, particularly at TELNEC, Laboratorio Nacional de Engenharia Civil in Lisbon. And so the story starts in 2017, when led by Professor Papanini, we applied to NH20 SEDA project to prove the efficiency of these such, let's say, integrated solution, low damage integrated solutions. We considered like 3 different test phases. We have tested, like, first of all, the structural skeleton to understand the behavior of the low damage bare frame, and then an option 1 that was practically the structural skeleton plus an internal gypsum partition with low damage detailing, and then the final one that was actually the integrated low damage solution with the facade in both directions and internally rocking infill masonry brick partition that went side by side. So honestly, this research project has been a milestone in our research career, because we had the possibility to collaborate with different partners, either academics or industry partners, and we have been involved, and we actively participate in each project phase, from the early stage design to the post-processing, that despite we drafted 6 articles is still ongoing, because you are deeply studying the dynamic behavior of the specimen yet. And so we started with the design, of course, of the structural skeleton, and subsequently, of course, the connection and the structural details. And then we saw the components birth in the supplier's factory, what we also follow with the pre-assembly of the components. And then we have been shipped in Lisbon, fortunately not by truck as the specimen did, but with an airplane. And there, of course, we have been involved in different tasks as instrumentation plan and the construction phases, of course, and tests up. And last but not least, of course, the experimental test. And then, as already said, the post-processing is still ongoing. Well, of course, the starting point, let's say, of our design is this modular large-scale benchmark building, from which we extrapolate a submodule, and using the Cauchy-Freud similitude, we scale it with a scaling factor 0.5, and we just got the main feature, the main like characteristic of our specimen, that, as you can see here, is practically splitted into main direction. So the frame direction in the longitudinal wall, while the wall direction in the opposite direction. So for the frame direction, is easy to understand that is a moment resisting frame, a low damage moment resisting frame made by timber beams connected to reinforced concrete column with post-tensioned cable at the center of the section, and or as Simona showed, and also plug and play dissipators at the edges of the beams. While for the wall direction, let's say, you can understand that the seismic resistance system is these 2 rocking CLT walls that were vertically post-tensioned with the dissipator at the base connecting the wall with the steel base plate. While for the slab, we adopted 2 different flooring systems. For the first floor, we adopt this TCC floor, so flooring system, let's say, so timber concrete composite flooring system that is practically made by parallel timber joist with a concrete topping, while the top floor, the slab on the top floor was a 3PT flooring system that we designed collaborating with the University of Canterbury, that is practically a timber concrete post-tensioned beam screwed all together. And then, yeah, this is like the seismicity we used to design the building. So we actually picked up 5 locations, 5 high seismicity location along Italy. And from the output, so from the mean spectra, we used an advanced design methodology called direct displacement-based design. And so we used like the target drift in the frame direction was 1.2, while in the wall direction 1.15. That's just, let's say, to be compliant with the shake table characteristic as maximum payload as well as dimensions, but frankly, also to be also to have enough seismic demand on the connections. And so of course, we arrived to the internal action, so, and we designed the connection, just drag it into sketches about the wall-based connection and the column timber, the column beam interface connection. So you can see here better that they present both a post-tensioned element in the center of the section, and then the plug and play acted like at the edges, dissipating energy. For the option one, so after many tests, of course, on the bare frame, when we coach like the behavior, we start building the partition of option one that was, as I said, bare frame plus this T-shape internal low damage fiber reinforced gypsum partition that was made by two main components: a sub-steel frame inside, and then gypsum board attached at the edges. So as you can see here, the damage we adopted, so internal decided gaps, and also disconnect the steel frame and the gypsum board as much as possible from the main structure, just to have less interaction. And here, the integrated low damage building system for the cladding system, so ZFRC, glass fiber reinforced concrete precast cladding, we use two different topology of connection, of course. One was a sliding connection that, of course, allowed the movement of the panel in the in-plane direction, while he avoided like the out-of-plane mechanism, while for the restrained anchorage, we used like this connection, so this steel plate nailed to the timber beam with this bucket filled by grout, while for the spider glazing, is worth mentioning that it was the first time that this system has been like tested dynamically. So we also choose them for this reason. And so let's say the expected behavior was just this rotation, this individual rotation of the glass panel due to a spherical joint that was in the rotool screwed in the spider connector. And here the last component that was this rocking internal low damage in filler brick partition. So as you can see that the principles are the same that we adopted for the gypsum partition. So we left some gaps, internal gap either at edges, so from the vertical stud to the column, but also we left some space from the top brick line of the masonry panel and the horizontal channel. And of course, is normal that we build the masonry panel inside the horizontal channel on the top of the first floor. So after this amazing design, I remember, and all these renders, the 1st April 2019 at 8:00 a.m., this huge truck arrived in Lisbon with all the components. And so we understand that, of course, we understood that the construction of the test building would start soon. And as usually, we start from the bottom. So just place these foundation steel plates on an existing foundation plate already available in the lab. So imagine that this existing steel foundation weighed 9 tons, and the maximum capacity of the shaking table was 40 tons. So barely the 25% of the maximum payload was just busy with the foundation. So it was another challenge that we faced. And so the construction phase, for the structural elements, we start uplifting the vertical elements, and we kept them standing using temporary supports, and then we just proceeded floor by floor. So of course we built the first floor, and then we put in place the beams of the top floor slab. Here, a bunch of structural details. I want to just focus your attention on the top left, where you can see how many instruments we used just to fully monitoring one beam column joint. While another thing that I want to point out is this fancy connection called bow tie that I'm really fond with, because, of course, bow tie, because you can understand by the shape of the steel plate, but it is part of the bigger connection that was wrapping like the slab, the wall, at the external beam edges, the external edge beams, as you can see here. So imagine this buttonhole, okay? and there were like a pin insert in, and during the rocking system, let's say the rocking motion, the wall was freely to move, and also this button will avoid the displacement compatibility from the slab to the wall and allow to transmit like the shear forces on the stories. So yeah, just a bit more about the details we adopted for the structural components. So as you can see here, this connection on the corner just to avoid the diagonal cracking, sorry, and also this connection from the gypsum board to the main structure, as already said. And then here we did also the finishing with the foam and so on. So here, of course, after the test, we demolished the previous, let's say, partition, and we start building the new one. So the masonry partition with the same, let's say, details that we used for the previous one. But you can see here we left some space from the brick to the horizontal channel, and it is how it looked like in the end. So here, I want to just say something about this detail for the facade, and also a funny story in the end. Just so here is the sliding connection we adopted for the cladding system, and this is the restrained anchorage that we, of course, adopted. Here is better to explain what I was trying to say before. So this vertical joint is inside this rotool, and then this device is screwed in this buttonhole on the spider glazing, creating this system that honestly is also really beautiful to see in the lab, but even in real buildings. And the funny story is that, of course, it's normal that you think that we build first the internal partition and the external facade, but once we did it, we realized that to check the status of the internal partition, we needed to get in. And of course, the only way to get in was the scaled door on the precast cladding. And honestly, it was water enough to don't have the possibility to get in. So Simona was in charge every run to put the stairs, get in with a light, check the status, mark the new cracks, and get out. It was just in charge to hold the stairs in place. So that's the woman power, let's say. But okay, just a bit more about instrumentation. So as already said, we used up to 78 instrumentation channels to fully monitoring the behavior of the building. And of course, considering load cells to monitoring the post-tensioned force in the cables as well as the bar, and then string gauges to live monitoring the stress strain of the dissipators, as well as accelerometers and LVDT, of course, to measure the relative displacement between, for example, the connection, the gap opening between the timber beams and the columns, and then accelerometers and optical devices to catch the global behavior of the building. Here a bit more the selection of the accelerogram. So we selected the 5 accelegrams just for the horizontal direction. These first 5 that were 2 near fault and 3 far field, while the 6th one was just used for the vertical excitation, and we scaled them to be spectra compatible with the 4 limit state that we have already chosen. And then here, imagine that for 3 test phases, and of course for 4 limit states, and for 4 accelegrams, we run this test protocol. So 3 unidirectional tests first, X, Y, Z, and then the bidirectional with the ground motion at 45 degrees, and then the T-directional one. But so in the end, the total amount of ground motion that we ran was around the 250, just because in the end we reduced the number of the ground motion for the option 2, but also for the higher level, we decreased the number of tests, just running the bidirectional, the 3-directional ones. here the best part, so the video, as you can see here, is the behavior of the option one building system, and here with an action cam we coach like the internal behavior, the behavior of the internal partition. And imagine that this partition usually collapse around 1% of drift. That means that we have the loss of the gypsum board, but even the buckling of the vertical stud in the steel frame, while here we reached like 1.32%, and the only damage we got was just this diagonal cracking due to the timber frame of the doors, while the perpendicular, like this partition that here is hidden, had no damage. So of course I'm a bit lying because we observed some damages. Of course, the dissipator, they, as Simona already mentioned, has done to be like stressed and replaced. While we've got also this double shape deformation of the steel plate and the end of the gravity beam that was spanning in the center from the frame to the other frame, just for the vertical excitation. While also we observed some disconnection from the slab to the top floor. For the non-structural component as well, so I already spoken about the gypsum partition. We have a loss of planarity, let's say a principle of autoplane mechanism in the glass facade, while this is funny because we had just one loss of mortar in one brick in the masonry partition. So here, just few experimental results. On the left, you can see just the global behavior of the building in terms of acceleration and interstory drift. If you remember, I say that we designed the drift, so we designed the building for a target drift around 1.2, 1.15%, while the behavior was we reached was twice the expected interstory drift for the skeleton building. That means that of course, for the cumulative deformation on the dissipator, but that means that the system was highly reliable. And here some secondary spectra about the top floor in the frame direction that we used as input demand for the structural components. And here the proof that we let's say haven't got any damages on the structural components, in particular these two dots and dashed lines are about the glass facade and the cladding, while what you can see, this decay, is due to the settlement of the bricks in the channel that was on the first floor. And so we are at the last slide, because we managed to build up a numerical model, a lumped plasticity numerical model, as already mentioned by Simona, but just of course you can see that it catches very well the behavior of the building, also from the global response here in terms of interstory drift at the second floor. And so this is really important, because as conclusion, so I want to just say that this advanced, the advanced, of course, seismic performance of the test specimen that I've shown you in this previous slide prove, of course, the efficiency of this integrated solution. But I want to also highlight that the advantages that we had also in terms of time of construction, because of the modularity of the system. No, so this Lego system that is very simple to build. And also that is really important that we can accurately predict the seismic behavior of such building, just because if you want to spread this technology, also professional engineers, all the engineers has to be capable to design and predict the building behavior, of course. And here we are. So the final remarks. I want to just point out this sentence, because for me is really important, because think about the modularity of this system. We can easily, for example, rearrange the internal spaces due to the modularity of the system as well. So we can achieve like a sustainable approach from the design. And then another thing is that I spoke about a low damage integrated system. that is really important in 2021, but looking at the future, we need to include the seismic performance within a more general high performance approach that comprises, of course, the energy efficiency of the building, the other performance like acoustic and air ventilation and so on. So that's for me is really important at the goal we want to achieve in the coming future, let's say. So that's for all for me. Just a bit of reference of the last work we submitted, and thank you for the attention and for the opportunity, of course.
Thank you very much, Jonathan, and thank you also, Simona, for these amazing presentations. Both of you really clear and also presented us such interesting results of these amazing projects. So this is a really great opportunity for PhD students to be involved in such huge projects. And so having the opportunity to manage such experimental testing, large scale shaking tables, and also super innovative. So while people maybe I ask people to put their questions, if any, in the chat so we can have a bit of discussion with the speakers. I'm sure you will have a lot of questions and curiosities. And meanwhile, I can start just asking if you considered also the effect of aftershocks in this kind of system. So if you have any kind of concerns about aftershocks and especially about the plug and play systems, if any, I don't know.
Yeah, but imagine that in this kind of, let's say, test, it's very hard just to run the ground motion, the aftershock, because you are doing many tests in sequence. So every test can be an aftershock of the previous one, just because we used the same dissipator for more than 20 tests. So imagine that what was called the deformation that we've got in the dissipator in the end was just cumulative cumulative deformation due to a simple thing that we use the same dissipator for different runs. So of course the answer is yes, every run can be like tagged as an aftershock.
Perfect. Okay, thank you. And about the, okay, oh, we have another question from the chat. Okay. So from Masoud Gamari, thank you for your informative presentation. How did you take the 3D effects into account in the Lambert plasticity hinged models?
No, honestly, we didn't take it into account yet. No, honestly, we didn't take it into account yet in that model. Honestly, yeah.
Okay, but are you going to do that or just studying the single elements?
Let's say that we have some ideas. Of course, we need to model in another way the slab just to take it into account on the flexibility and the vertical direction, and we are thinking about it. But of course, with the Lambert plasticity model, I think that there are different possibilities to do it, but we'll see.
Yeah, because I want to add that at this point we only developed, let's say, this 3D model in Romoco, considering just the behavior in the two different directions and focusing on the structural part only. So there is a lot of work that is still ongoing because we would like also to include the contribution of non-structural components in addition to the 3D effects into these models. So it's a lot of work, let's say, because we started with this test, at least with the design, in 2017. So imagine, and there is still a lot of work that we are doing. So
yeah,
to give you an idea.
This is innovation. Okay, thank you.
That's for sure, but we are two people, so
we need more PhD students then. Okay, we have a question in the chat. Maybe yes, it's only for me, but I will read for you. So from JGC, have you considered the carbon footprint of those systems in comparison with others?
Yes, of course. It's something that we are still working on, and there is many works that say that, of course, is one of the goals that we want to achieve, of course, and it's something we are exploring also with the help of master students, and is one of our research objectives, of course. Yeah. But of course, as you can imagine, you had just steel plate to the connection. So let's say the impact you have using timber, let's say, rather than concrete is much higher than just introduce the steel plate on the connection. So we can see a bit of variability just switching like the structural frame, let's say. So for example, from a traditional one to a low damage one, but of course, we just make a step more if we consider timber. That's the point.
Okay, Simona, you were adding something? I don't know.
No, Jonathan already did. Okay.
Perfect. Okay, any other question? Don't be shy, you can write in the chat. This is an open forum. We are all almost young, so okay. And what about other cascading events, for instance, like fire, using this kind of connections, or steel connection, timber beams? Do you have any kind of, you can have any kind of issues, or you, I don't know, prevent, I don't know.
But,
well, it depends. For example, just sorry, Jonathan.
okay.
Talking about no structural components, for example, on the gypsum drywall partitions, the first campaign which was developed to study this low damage solution was carried out in New Zealand at the University of Canterbury, and there they include within the detailing a proper let's say detail to take into account the fire aspect. So we are still working on these, not only about fire, but especially looking at the energy efficiency of these solutions. Because of course, if you think we are including seismic gaps, which are fundamental for to have at least higher performance in terms of seismic response, but these could bring to higher, for example, energy consumptions. So we are working especially during this period and in the next months and years maybe on this topic. So to create a fully integrated, let's say, multi-performance with high multi-performance solution.
Okay, thank you. We have another question in the chat from Gerard. Hi, Gerard. So thanks, guys. Great presentation. Just a quick question. Would you see this type of plug-and-play system more suited to new construction, or also a possible retrofitting measure for deficient existing buildings?
Well, we are working also with this solution for retrofit of existing building. So imagine if you, let's think about an obvious thing.
Selective weakening.
Yeah, but also if you have to, for example, create a building, a global intervention by adding a new wall. Why not creating an innovative low damage wall instead of a monolithic one, for example? So yes, sure. And apart from this, also considering for example, for non-structural component also, we can include some innovative detailing in existing buildings. So yeah.
But in that case, you have some problem with the residual displacement, because you don't have that internal cable, that pre-stressed cable to avoid and recenter, I would say, the structure. So I don't know, if you use plug and play on an existing structure, you can have any kind of issue with residual displacement or not, in your opinion?
Yes, I think so. It's like BRBs. Of course, the damage is concentrated in like little device rather than in a big one that is the BRBs. But yeah, it works like tension compression. So it's going to be like completely damaged at the end, and you can get your residual deformation. Of course, you have to put something in place also that give to the structure the eccentric ratio. So of course, what I was mentioning is the selecting weakness. So imagine you have a shear wall, you can cut him in the like a section cut at the base of the wall, and you can put external dissipators and maybe something like post tension in the external of the wall. So there are something that has been already written in the literature, especially from University of Canterbury about it. So yeah.
Okay, thank you. We have another question from Ludovica Pieroni. Hi, Ludovica. So thank you for the interesting presentation. I have two questions regarding high-rise buildings. So did you apply low damage devices in all columns bases and beam column joints? This is the first. And have you ever evaluated the optimal placement of a limited number of low damage devices within this type of structures?
So so the answer of the first question is no. At the base of the column, the words like normal plastic hinges, but of course the total eccentric ratio of the building is weighted among the connections. So just the plastic hinges on the base doesn't influence it so much. While for the second question, no, but we are working on standardize the connections, saying that if you have a bending moment that goes from 1000 kilonewton, 100 kilonewton meter to up to 500 kilonewton meters, you can use trip back and play with this diameter. So that's what we are working on.
Okay, I don't know if Simona wants to add something to this topic or to this question.
Oh no, Jonathan said everything. I'm thinking about the other question, which is about the optimal placement of a limited number. Well, we have not developed this type of, let's say, specific study yet. But at the end, it depends a lot on the type of structural system we are considering, and especially on the seismic performance we want to achieve. So it depends on a lot of on a lot of things. But it could be a good thing to develop in the future. Why not? This could help and create optimal, let's say, for configurations for these low damage solutions.
Okay, then we have another question from Giovanni. Can you apply low damage technologies to other disciplines beyond buildings?
Wow, cool.
Yeah.
Yes, of course. Because it's like a low damage philosophy. So low damage is something that is easily replaceable. It's something that is not going to be damaged in the end. It's something that can enhance the resilience of the system we are designing. So the answer of this question, I think that is yes, we can develop it.
And especially about bridges, not me and Jonathan, but our professor is working with other groups, other students or PhD to develop this solution focusing on bridges. So there is a lot of work already.
Okay, then we have a question from Masoud Gamari. So we lost many people due to the collapse of non-structural elements in Iran, Kermanshah earthquakes. And as a suggestion, you can explore the toll rate and the scientific reports. Okay, I don't know if you...
Okay, thanks for the suggestion.
Thank you, and from Andri Setiawan, hi Andri, so thank you very much for the interesting presentation. Is the proposed low damage system also capable to reduce the floor acceleration, or is it mainly just to limit the damage related to the drift, so displacement?
Well, in this case, it depends on the low damage solution, let's say, because we do not, it depends, let's say, on the specific aspect we want to study to look at the floor acceleration. If you see, when I explained the EQ-ROD solution, in this case, obviously the introduction of this supplemental damping would lead to reduce the floor response, let's say, floor spectra in terms of absolute acceleration. So we are working, for example, we did some investigation for our SERA project in terms of absolute floor spectra. And at the end, let's say that these help a bit, but we need to work more if we are thinking about, because we focus on only, at least in our case, on drift sensitive components. So we developed with this floor acceleration to give some indications on the expected floor spectra we could have in these cases. So this could be useful if we want to study these acceleration sensitive components. So this is just to say that it can be, if it depends on, we have to design our proper system is if our objective is this one, let's say. So of course, we can, by including syndicating, we can do this.
Okay, perfect. So I don't see any other questions in the chat. So I think we can also close the webinar. So thank you again to both of you, Jonathan and Simona, for your time and your presentation. And also thank you to all the audience for the interesting questions in the chat and for being here with us today. So please follow us on our social channels and don't miss the next webinar of the series Concrete Affairs, which is about the beam column joints and modeling retrofitting strategies for these elements on existing concrete structures. And thank you. Thank you very much.
Thank you too to invite us to join.
Bye-bye.
Bye-bye.
Bye-bye.